Today, we're going to learn about torque, power, and speed. Now, shafts are rotating members. Usually, they have a circular cross section and they're used to either transmit power or motion through a mechanical system. Um, the shaft provides an axis of rotation or oscillation, and it can have many different elements. There can be gears, pulleys, flywheels, cranks, um, bearings, and other types of geometry that help to control motion or even induce motion within a structure. An example of a shafted mechanical system is a jet engine, um, where there's a central shaft in that engine. There's a series of bearings, which could be thrust bearings. There's a series of compressor blades that act to compress air. There's a combustion region that injects fuel into that compressed air and ignites it. And then there's the turbine end, where those hot gases pass over these turbine blades, spinning up the shaft, generating either thrust or electricity, right? So this is a very, this is classic example of shafts that we see in design. Now, an axle is a non-rotating member that carries no torque and is used to support rotating wheels, pulleys, and the like. So shafts are rotating and axles are non-rotating. Now, torque. Let's remind ourselves of what torque is. Torque is a moment that causes a twisting deformation about an axis. So if we had, say, a cylindrical shaft and we applied some torque about the shafts along the shaft's length, then it will induce a twisting motion, an angle of twist, and deformation from one end of the shaft to the other end of the shaft, right? Now, torque, when we think of its impact in the state of stress, induces torsional shear stresses, where torsional shear stress, tau, is equal to the torque times the distance from the neutral axis at which we want to calculate that stress. Meaning if we are on the outer edge of our body, the torsional shear stress is the highest, and divided by our polar moment of inertia of our cross section, right? So that the maximum torsional shear stress, torsional shear stresses are maximized at the outer wall, at the furthest distance from the neutral axis, so the outer radius of our shaft, right? Now, it's often necessary to obtain the value of torque, so the moment that's applied to a shaft, from a consideration of the shaft's power and speed as it is rotating. And so the relationship between power, torque, and speed is very important in shaft design. Now, in English units, we can define power as horsepower. And then there's a couple of different ways that we can calculate that power in terms of horsepower. It could be a force times a velocity divided by a factor. It could also be defined as a torque times the shaft speed in rotation per minute, with a certain factor, or that same set of parameters divided by a different factor. But in essence, we have the relationship between torque, between power, torque, and the speed at which our shaft is rotating. Now, in metric units, it's a little bit simpler. Power is in terms of watts, and that power is equal to the torque times the angular velocity. And here, this should be in newtons times meters here, our torque. We also could define it in the angular velocity in terms of rotation per minute, where torque is equal to a factor times power in watts divided by the torque in newtons times meters, right? Now, how does this then relate to shaft design? What is this relationship of power, torque, and speed? How does that impact the design of a shaft? Well, let's take that core example, the core equation that power is equal to torque times speed. This equation highlights a critical trade-off. For a constant power transmission, if speed needs to increase, then the torque must decrease or vice versa. So if we want more speed, we need less torque in order to maintain the same power in our system. So if we're power limited, our motor that's spinning up the shaft has a certain amount of horsepower, we have trade-offs between these two parameters. But also the inverse relationship is paramount in shaft design. If we were to design a shaft, we wanted to size the shaft, we also have to consider the material properties and the limits of those properties and the stresses that can be induced in a shaft. For instance, say we have a high power but low speed application. If we have a high power and a low speed application, the torque required in our design is very high. For that high torque to be sustained in our design, we think that torque also impacts the torsional shear stress that's induced in our design. If this torsional shear stress is limited by the strength of the material, then the diameter of the shaft must be very large in order to accommodate that big torque in our design. So this kind of highlights that in order to size the shaft properly, we have to consider what power we're transmitting, what speed we expect the shaft to spin up to, and then size accordingly to the material limit of stress and the dimensional, and then end up with the dimension of our shaft's design. And with that said, we've got the basics of the relationship between power, torque, and speed.